My name is Sai Tirunawala, and welcome to my Constant Velocity Lab. This is just a table of contents. It just comprises of everything I'm going to cover. And now onto the introduction. The goal of this experiment is to compare the measured motion of an object moving with constant velocity to the predicted motion generated by a computational model. By doing so, we can essentially evaluate how well theoretical models align with real-world data. The object I used was the Pascal cart, and I observed the motion using the tracker software, and I generated a model using GlowScript. And through the comparison between the observed and the ideal model, the lab highlights fundamental ideas behind Newton's second law of motion. So what is Newton's second law and how does it relate to momentum? The law basically explains that the net external force on a system is equal to the rate at which its momentum changes. In other words, force is directly related to how quickly momentum varies over time. So the bottom just depicts how F net is equal to the change in momentum over the change in time, but it's also equal to uh, the equation where the initial velocity plus the net force over its mass times the change in time equals to the final velocity of an object. So for the procedure, I used a Pascal cart and rolled it down a flat surface and recorded with the stationary camera. I then used Tracker to mark its positions and graph its position behavior. I then used GlowScript to model the cart's motion under constant velocity. And then I entered the observed and predicted data into a spreadsheet and graphed a position versus time graph, including both of them. And then I compared the graphs and evaluated the model's accuracy, noting possible sources of error. This is the video I used for my experiment, and as you can see, the red dots are tracking the cart's position at each time increment. On the top right, you see the position versus time graph, where it's almost, it seems linear, but slightly not. And then for the initial velocity needed for the model, I used the first time step as a reference point, and I calculated it to be 0.417 meters per second. So for the computational model, I used the starter code given by the lab, and I changed four main things. The first one was the position, which I set to 0.003296, and the initial velocity, which I set to 0.47, and both these initial values have zeros for the y and z components because there was no movement in that direction. The second thing I did was the time step where I set delta t to 1 over 60 since the video was 60 frames per second. And the third thing I did was I set the net force equal to the zero vector since there were no forces applied onto the object. The last thing I did was I applied the momentum principle from Newton's second law to derive an equation for velocity and position. And basically this just means that I use the velocity update formula and the position update formula to calculate the correct positions and velocity for the computational model. So this graph shows the difference between the observed and the computational model. The computational model obviously has a strictly linear pattern to it, while the observed model has a linear pattern up till like the halfway point, and then after that it starts to curve downwards due to external forces acting upon it throughout the entire time, and it starts to show at the end. So sources of error, obviously drag and frictional forces. Even though the experiment assumes constant velocity, small amounts of friction or air resistance can act on the cart which I used and slightly slow it down, which did happen. And the tracking software, while marking the cart's position in tracker, errors can and did occur when the point mass was not selected accurately. This leads to slight differences in the measured data points, deviating the data. So for the analysis questions, these were my answers. The first question was, what would happen if the positive and negative x directions were swapped? I concluded that the main change would be that the slope of the graph just reverses in sign. So instead of a positive slope, it would become negative. And then what if the net force was truly zero? And if so, how many forces combined to give that result? So although the model does assume that the net force is zero, the experimental data shows slight differences at longer times, which indicates that additional forces such as drag and friction were acting on the cart, and these resistive forces reduced the accuracy of the assumption and showed that the true net force was not exactly zero. Thank you for listening.